warm-up. We are now ready to begin. Get current slide, and we are ready to go. First, any questions, anything we've covered so far? Chapter 12, 11, 12, or the first part of 13? All right, that'll be fine. Okay. And all three of your classes, you've got a test in hand now, don't you? Yeah, I thought so. Okay.
Have you given us one for DQ?
Maybe not. Maybe I've made that out, but I haven't given. Yeah, haven't given it to you yet. Okay. It will be soon. Tomorrow you'll have.
Hopefully I'll give you one back tomorrow.
Okay, good. All right. We started, if there are no questions, we started 13.2 last time. This is now talking about the calculus of these vector value functions. 13.1 was basically looking at what vector value functions are. And we covered real quickly last time the limit of a vector value function. Same thing I think you would expect to see anywhere. Here's theorem 1. Vector value limits are computed component-wise. Now, to me, this looks almost a little fuzzy, is it, or is it clear enough? This is this automatic. Does that get any better?
I don't think so. Or is it maybe picking up the chair in front of it?
Something down here. I don't know. Here is a focus thing. What is interactive mean?
You can go to the right or to the left with it. So to the right or to the left. Yeah. Keep
Does
going.
that do anything?
It's making it fuzzier. Go to the left.
Huh?
Go to the left.
Can you tell anything happened?
Yes.
Oh, it is. Okay. Keep going left, or is it? Okay?
Left one more. And one more. That's good.
All right. Left one more. Is that worse?
That's good.
Is that worse?
It's getting worse now.
Okay, now. So I'll go back. I want to get worse once.
Yeah, that's good.
That's good. Okay. I think it exits itself.
There it goes.
There it is. Okay. All right. My old eyes couldn't tell much difference in any of those. All right, so what this is saying, vector value limits are computed components-wise. Vector value function, R of t, still looks pretty fuzzy to me, but it's x of t, y of t, z of t. It approaches a limit as t approaches t0 if and only if, this is a both-way thing, each component approaches the limit. And in this case, that would be the limit of R of t as t approaches t0, exactly what it's saying there, is the vector whose first component is the limit as t approaches t0 of x of t as t approaches t0. The y component, the limit as y of t approaches t0, and the z component would be the limit as z of t approaches, the value z of t as t approaches t0. So the limits are of the entire function are the function is the vector of the limits. Okay, I guess you would say. And Matt's here. All right, good deal. We got half, well, not quite half the class here. Close to it.
Only half a person.
What's that?
So only another half person.
Yeah, then we will on the notes or wherever the split is. Okay. So let's take. This is part of the proof of that, I think. Yeah. The proof is you start by letting u of t be some vector ABC, and consider the length of the square of the length of, well, let me blow this up some. Why I didn't blow up the other one, I don't know why.
Maybe that's why it's hard to see.
Yeah, maybe it was. Okay.
697 in the new book.
Yeah, sorry about that. And this is Jonathan, right? Okay, we're more than half the class here then. All right. Huh? Yeah. Oh, both of you might need one. Do you think? Okay. And again, this time I will put this on Screencast-O-Matic. The first question is from 11.1. Yeah. Second question from 11.2. The third and fourth questions are from 12.1. Number 5 from 12.2. That has 3 parts. The 6 is from 12.3. 7 from 12.4. 8 from 12.5. 9 and 10 are from 12.6. All right. Okay. So, what we just had before vector value limit, I think that is a little better, are computed component-wise. A vector value function, R of t, which is x, y, z, all of t, okay, approaches a limit as t approaches t0 if and only if each component approaches a limit. And what would those be then? The limit of R of t is t approaches 0. Remember, R of t is a vector, okay? So its limit has got to be a vector. The first component of that vector would be the limit of x of t as t approaches t0. The second component would be the limit of y of t as t approaches t0. And the third limit of z of t. And the third component would be the limit of z of t as t approaches t0. Now, how to prove this? The first step would then be let u be some vector ABC. Vector, okay? Those are the 3 components. And consider the square of the length of that vector u. Okay? Now, this is the square of the length of that. Of the vector between R of t and u. Okay? The difference between those two. Okay? Vector R going somewhere, vector u going to, what's the difference between the square of the distance between those 2 vectors, okay? That would be component by component, x of t minus a squared, y of t minus b squared, z of t minus c squared. That's the component of this one, or x of t is the first component of this, a is the first component of this, so that'd be first component, different square, the second component, okay. So that would be that. Now, those are, now if you took a limit, let's see, I want to get ahead of it. This approaches 0 if and only if each one of those approaches 0. Because if one of those is not approaching 0, no way this one can, because if one of these is approaching something else or getting infinitely big, it can't, because you're adding something going to 0 for 2 of them, or maybe only 1, and then the others aren't. No way. For this to be approaching 0, each of those has to be approaching 0. And that basically is enough to prove what the theorem was calling for. So that's the theorem. Let's do actually an example with it, okay? We're not quite ready for that, so let's do the example here. Calculate, and the theorem is far more wordy and in some sense a little more complicated than just doing it. So calculate the limit as t approaches 3, if I can read, of r of t where r of t, vector value function r of t is t squared, 1 minus t. I think I've seen this one before, haven't we? And t to the minus 1.
That sounds familiar.
Say again?
I don't know, I think it sounds really familiar.
I'm sorry, I can't hear.
It's almost similar to one we did, but not quite.
Yeah, I think that it looks very similar. So what would this limit be as RT is approaching 0, as t is approaching 3? 9, comma, negative 2, comma, 1/3. Okay. That's it. You just plug it in, basically. Okay? Now, there's another issue that we sometimes deal with. Continuity of vector value functions, defined in the same way as in a scalar case, when you're dealing with scalar functions. Vector value function r of t, which is x of t, y of t, z of 0, is continuous at some point t0 if the limit as t approaches t0 of r of t is r of t0. In other words, this one was continuous there because that limit did exist there, okay? And the value of it is that, r of t0, okay? Now, that's all they say about all that. Now we get into the calculus type stuff. And the first of these things is, what's the first? After we fiddle around with limits, what's the? Yes, we take a derivative, and that's what we do first. How you take a derivative of a vector value function, you take the derivative of each component, which basically is this. R prime of t would be then the derivative of r of t with respect to t. That's what that means. That's the definition. And that would be the limit as h approaches 0, just like we did before, r of t plus h minus r of t divided by h. An indefinite integral, as long as it's continuous, can't have any gaps there between r of t plus h and r of t. If there are, limits not going to exist. But as long as they are, as that exists, that's what we define the derivative of r of t to be. And you do that, guess what? Component by component. There's nothing really too new here, okay? Now, we also say that r is differentiable at t if that limit exists, the one that's right there. Notice that the components of the difference quotient are themselves difference quotients, okay? You can't see it here, but it's in your book. I don't think they show this on the slide, but you just do that same thing for each component. The limit as h approaches 0 of x of t plus h minus x of t over h, comma, limit, y of t plus h. Each of those is, so you basically, derivative of x of t, comma, derivative of y of t, comma, derivative of z of t. And that leads to theorem 2, which is vector value function derivatives are computed component-wise. A vector value function r of t, which is x of t, y of t, z of t, is differentiable if and only if each component is differentiable. And in this case, the r prime of t would be d by dt of r of t, which is the vector x prime of t, comma, y prime of t, comma, z prime of t. Take the derivatives of each component. Now, each component has to have a derivative. Each component has to be continuous. It has to be differentiable. Vectors here. This is, we're talking about vectors. Okay. Yeah, this whole chapter is. Okay. Good to see the crowd coming. Of course, it's still all Y chromosomes, which is okay. So, theorem 2, vector value function derivatives are computed component-wise. There are a couple of examples here. Of course, when I go to write them, this is going to shrink, so I'm going to get it to shrink. Okay. What is d by dt? Goodness gracious, this thing is cranky. Of this vector, t squared, t cubed, sine t. Number 1, can you take the derivative of that vector valued function? Sure you can. These are all continuous functions, so what would be the derivative? Also a vector, by the way. A little louder. 2t. This doesn't evaluate any particular place, just in general. Got the 2t. 3t squared cosine t. Very good. Okay. How about this one? d by dt of this vector value function cosine t minus 1 e to the 2t. Well, can you take that derivative? Sure. What would it be? Negative sine t, 0 to e to the 2t. Got it. Now, if you gave you any particular value to do it, you do it there too. Okay? Now, higher order derivatives are defined by repeated differentiation, and every time you take a derivative of a vector value function, you get another vector value function. Okay? So it keeps going. So r double prime of t is the same as d by dt of r prime of t. Okay? These are vectors, by the way. Okay? R triple prime of t is d by dt of r double prime of t, each being another vector function. Okay. Now, example 2. Let me start over from a clean page. Okay. Calculate r double prime of 3 where r of t is equal to log t squared. It's an equal to, that's a pretty ugly equal to. Log t, I forgot what I said, yeah, log t squared. Yes, and that would be r prime of t. And by the way, please folks, remember, take derivatives of the function of t all the way, and at the very end do you plug in r of 3. And I didn't even write that down. It's supposed to be r double prime of 3. Okay, sorry, not of t. That sounds alike, but it's not the same. Okay. Well, okay. This is r double prime of 3. We take the derivative with respect to t all the way, and then at the very end plug it in. So this would be what? R prime would be 1 over t, 1, 2t. How about r double prime of t?
Maybe 2 over 2t? Or t squared 2?
Okay. I would rewrite that first one. I was starting to suggest this. Write it as what? That first component.
It would be negative 1 over t squared.
Yeah, t to the minus 1, 2t. Especially if you're taking the derivative, I definitely get it in exponential form rather than quotient form. All right, Ashley's here. Good deal. What a good class today. We're right now only missing Tony and Javon. And Javon was in a pretty serious, it sounded like, car accident, and he came by one day last week, but he was not doing too well. He has pretty bad nerve damage in one shoulder or arm or somewhere, so I'm not sure he's supposed to be driving, and he comes from Tuscaloosa, so hopefully he's following this online. Let's first calculate R double prime, now that we have R prime, but I would say use this form of R prime. What would this be? I think I heard you say? Negative 1 over t squared. This time it's all right to put it that way because we're not taking another derivative. Otherwise I'd do it negative t to the minus 2, but you're okay. Next, 0, next, 2. Okay? And what is R double prime of 3? Is what? Negative 1/9, 0, 2. Very good. Let's see if the book got, yeah, they got it right too. Good for them. Okay. Now, that's how you take vector value derivatives. I'll leave it up there a little bit. Another advantage to having more of you in the room, it kind of heats the room up a little bit, I think, because this room was pretty chilly earlier. So think real hard, folks. Burn some calories, okay. What's that? Create. Yeah. All right. They keep on coming. This is good. All right. Tony is here. We have everyone except Javon. And I was telling the others that Javon was in a pretty serious car accident, so he may not be okay to drive yet. So we don't know. But glad to see all of you here that are here. Okay. All right, to move on. All right, here are the differentiation rules. And hopefully they would be what you would expect. Okay. Assume that R of t, vector value function, R1 of t, some other vector value function, R2 of t, some other vector value function, are all differentiable functions. Then, if we're adding, we're taking the derivative of the sum of two functions, R1 and R2, then that's the same as the derivative of R1 plus the derivative of R2. Shorthand for that would be derivative of the sum is the sum of the derivatives, just like we had in scalar functions. The constant multiple rule, for any constant c multiplied by any function, R of t, say, then the derivative of a constant times a vector value function is that constant times the derivative of the vector value function. Basically, the scalar constant rule, you might say. Product rule, yes, we love it, don't we? For any differentiable scalar function f of t, if you're doing the derivative of the product of that f of t times a vector value function r of t, then that gives you, what would you expect?
The derivative of one times the other plus the derivative of the other times the first?
That would be it. They do the first. F of t times the derivative of r of t, which now, remember, r prime of t is a vector. This is a scalar function. The product of that scalar function times that vector function, that r prime, plus f prime times your r of t. Exactly like you said, the first times derivative of the second plus the second times derivative of the first. Okay? And then also the chain rule, which, by the way, we've already been using. Pretty sure we did in one of those examples. for any differentiable scalar valued function g of t, then d by dt of r of g of t, well, we didn't quite do it in this form, but it's still the same, would be, I like to do this one first, r prime at g of t, then times g prime of t. They like to write the g prime in front, which is fine, times r prime at g of t. Okay. I guess I just learned it the other way and usually do it. But then you usually put the scalar values in front, so good reason for doing that. All right. Now they do show a little bit of a proof here for at least one of those. That's the adding. No, the multiplicative. No way, I'm looking at the wrong page. Sorry about that. Okay. Yeah, the proof is of the product rule. Sorry, I was looking at theorem 3. I said, we haven't done that yet. Okay. And I don't believe they have a slide of it, so, but it's a pretty straightforward. Maybe there's a little trick. It's the same type of thing we did with scalar functions. Okay, not quite, but it's similar. They just changed the vector function, and they did it easier. We'll just do it in the plane, not in space or in space, and they just did the product of f1 of t times the vector x of t, y of t, those are components, and then multiply the f of t in, and then you take a derivative of those scalar functions using product rules there. So it's just pretty straightforward, just like we did for scalars. In fact, you're dealing with scalars. Okay. Now, before we get to example 3, before we get to theorem 3, we'll do example 3. Let's let r of t be t squared 5t 1. That's r of t, vector function. And f prime of t, f of t, scalar function, e to the 3t. Okay? Calculate a first, d by dt of f of t, r of t. Okay. Good old product rule. And what would that be? Either way you want to do it. Okay, you want to do f prime of t times r of t, f of t, r prime of t. The order doesn't matter here because it's a plus in between. There's no difference. Doesn't matter which way you do. What does that come out being? 3e to the 3t. That's f prime of t times this vector function, t squared 5t 1 plus e to 3t times, what's r prime? So again? 2t 5 0. Okay, we can carry that another step, and what would that be? Okay, 3e to the 3t times t squared, comma, now, that was perfectly fine, but I just don't like the way it looks. So I'm going to change this ever so slightly to be 3 t squared e to the 3t. Okay. Next, 15 t e to the 3t, comma, 3e to the 3t, plus, that was 2t e to the 3t. Is that what you said? I can't hear. Okay. 5 e to the 3t. Is that what you said? Okay. Yeah. Okay. 0. Okay. Then you can add those two together and get you, it looks a little strange, but it's doable, 3t squared plus 2t e to the 3t, comma, 15t plus 5 e to the 3t, comma, 3e to the 3t. Close. Okay, sorry, they sort of cross up on each other, but now, is that the only way you can write it? No, you can write it dozens of different ways, which
You probably just keep the
Huh?
3T out of it.
I would like to do that, and I don't know if they do or not. There it is. I lost it there. No, they keep it in, but they write it at the end. No, they did it where I did. 3t squared plus 2t, in parentheses, e to the 3t, comma, 15t plus 5, e to the 3t, plus, comma, e to the 3e to the 3t, close angle bracket. All right, and now the B part. So I think I'll go on and erase this one if it's okay. Have y'all got it? Everybody? Okay. Huh? Oh, got it? Okay, I thought you said what? I can't.
The menu's in the way.
Oh, really? What is it doing? Oh, anyway, okay. Sorry about that. And this line here probably should have been at the bottom. I was afraid it was going to hit the margin and then disappear, or knock me out of the slide, so I moved it up there. I was hoping I could scratch it, but I couldn't. Enough to reread it. Got it, everybody? Okay. So let's do the B part. Okay. That was product rule. Now we'll do chain rule with it. By the way, this is unbelievably faster than this morning when I was trying to erase something on the slide. It was pathetic. Okay. This is the B part. D by dt of R of f of t. I can't write. Say it right and write it wrong. R of f of t, 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 t. Okay. I put extra parentheses in there. It doesn't really matter. Not necessary. So how would we do this? Second? Okay. And what is the derivative of f of t out front? 3e to the 3t. Okay. Okay. Would it be helpful to write out what we're actually doing here? That would be what you said, f prime of t times r of r prime of f of t. Okay. So we've written the f prime. Now,
So do we need to take the derivative of r and then plug f of t in?
yeah, where you see a t, you put f of t in its place, which is e to, okay,
So the first one would be 2
2t f of t. No, I'm sorry, you're right. You put the f in where the t was, okay. 2, yeah, which is e to the 3t,
and then 5 and 1. Or 5 and 0.
5, yeah, comma, 5, comma, 0. Okay. Now,
Just go ahead and distribute the 3e to the 3t.
what's that again?
Distribute the 3e to the 3t.
Yeah, and you put that on the inside, and that would be what? 6 e to the 6t I hope that's what you're saying. I can hear you talking, but I can't make it out. 15 e to the 3t, comma, 0. Yeah. Okay. And let's see if they got it right. Yes, look at them. They got it right as well. Very good. Okay. I'm just used to taking the derivative of the first, but then plugging the f of t in there. See, for me, it would have been better to do this. At this stage, write that as d by dt of, and probably not even quite that way, oops, hit the wrong button. Okay. Of r of f of t would then be e to the 3t squared, comma, 5 e to the 3t, comma, e to the 3t. That is, no, I'm sorry, that's just a 1 there. I was going to say that won't work. That's a 1. Because you plug in place of the t, you're plugging in what f of t is. So f of t squared, 5 times f of t, 1. Okay. And then take your derivative of that, and basically it works out being the same thing. This would be 2e to the 3t times 3e to the 3t, so that would be, add another 3t here. I mean, it's messy, but it's still doable. Comma, this is all a vector, 15e to the 3t, comma, 0. Okay, and that's the same thing we got, 6e to the 6t. That first one is messy, no matter which way you do it. 15e to the 3t, 0. Okay, you just have to remember to do it. And in fact, on this one, I think it would be even better to make this e to the 6t right there. Okay, and then it's a piece of cake. You know, you're doing the same thing. You're doing r of f of t. Everywhere you see a t, you put f of t in its place. And that, to me, then it's just easy to do. Some problems might be easier to do the way we did it there. I don't know. I can't think of any now, but they may be. But this one, to me, was far easier to plug in what f of t is on the r of t, and then you just do the derivative of that. Like I said, there may be other examples. It's what I try to do is minimize the places where I tend to make errors. Okay, I know when I tend to make them, so if I can minimize those, I have a better chance of getting it right. Okay, so that was example 3. There's the B part done. Okay, now I think we're ready for. Oh, and by the way, they said. Okay. I thought they were saying something beyond, but this is what we're getting to next. There are 3 different product rules for vector value functions. What? Okay. In addition to the rule for a product of a scalar function and a vector function, R is stated above, there are product rules for the dot products and the cross products. Okay? Those rules are very important in applications, so I think that's what's coming up next. Let's see. Yeah, here's the product rules for dot and cross products, as well as product rule of a vector function by a scalar function, or scalar function by a vector function. Okay, so now again we have R of t, R1 of t, R2 of t, are both differentiable functions, vector functions. The dot product, the derivative of the dot product is, hopefully, just like you would expect it to be, the first times the derivative dotted with the derivative of the second, plus the second dotted with the derivative of the first. I said them backwards, but guess what? In dot products, it doesn't matter the order. Okay? So, whichever way you want to do them, it's doable. Notice, this should result in a scalar. Okay? Could be a function of t. So your derivative would have that. This results in a scalar, the sum of 2 scalars. So yeah, you still get the scalar. So everything should work out pretty well that way. Cross products, on the other hand, don't fiddle around with the order. Make sure you keep the order correct. Okay? So d by dt, derivative of the cross product of 2 vectors, is the first, and which of these? Sums, it doesn't matter, but the crosses, it does matter the order. So you can do it either way. You can do the first, cross the derivative of the second, plus the derivative of the first, cross the second. That one you can't, like I said up here, it doesn't matter which order you do, down here it does. So therefore you might want to keep the order always the same, just so you don't do the mess up. But notice this will be, this is a vector, and the derivative of a vector is a vector. That's a vector, that's a vector. Cross product's a vector. Added to another vector, you still get a vector. So yes, at least the type of answer looks like they're right, and if you keep the order on the cross product right, you get the correct answer. Okay? Does that make sense? Goodness, I'm cold. All right. And they verify equation 4 for vector value functions in the plane. So in other words, they're doing 2-dimensional vectors, which is a lot easier than doing the 3. And you can take a look at how they do it, and sure enough, you come up with the same values. Now, in the next example, and throughout this chapter, all vector-valued functions are assumed differentiable unless they're stated, and it's pretty obviously they're not. Okay? So let's do example 4. I don't think there's a picture, so let's do it here. Prove the formula d by dt of, I don't know why I put bracket, but I think I like it better. R of t, because I have so many parentheses there, cross R prime of t is equal to R of t cross R double prime of t. Now, just looking at it, it wouldn't look like there's any reason for that to be true. Would it? But let's do it and see. Okay? What's that? Okay. So, first step, derivative of a cross product, what would that be? Okay, you're going to do R prime of t cross R prime of t. Is that what you said?
Yeah.
Okay. Plus.
The derivative, or it'd be the first regular.
Yeah. No. R of t.
Right.
Okay. Okay. Right. R of t
Cross the derivative of the second.
derivative of the second, which is R double prime of t. Okay.
I'm assuming the first one goes out
Why?
because they're both the same.
Okay.
And then that means they're
Parallel. They're the same vectors. And when you cross two vectors that are parallel or anti-parallel, the result is 0. Okay? So therefore this result, since those are exactly, identically the same two vectors, a vector cross with itself is 0. So sure enough, this is 0 because of property of cross products. Okay? Oh, that, by the way, is a 0 vector, okay, as opposed to the number 0, because the result of a cross product is a vector. Okay. Now, but when you add the 0 vector to any other vector, you get the other vector. All right. Now, what was one of the major things we took derivatives for? Back in scalar functions. Back in Cal 1.
equations of tangent line.
Okay, you were coming up with tangents. A derivative was the slope of the tangent line at any point on that curve. So the derivative vector R prime of t at t0 has an important geometric property. It points in the direction of the tangent to the path traced by the vector R of t at that point t0. Okay? Now, let's see what they've got here for us to do. Oh, they do have it. Yeah, look at that. I was hoping they were going to have this so I wouldn't have to write it. Now, what they're saying here is if you haven't noticed it yet, when you do write it in Leibniz notation, dr dt, okay? The independent variable is, I want to say, and I believe I'm certainly true at this, always a scalar, okay? Even if it's a functional value, it's a scalar function. It's the numerator, you might say, the upper part of that symbology represents the vector, the vector quantity. So basically what you're doing is a change of a vector quantity per change of its independent variable quantity. How much does the vector change with a little bit of a change of that independent variable, okay, that parameter. Okay. Well, going back to our good old definition of derivatives, or it looks like that, we're not at a derivative yet, but this would be R at just a little bit beyond t0, okay, t0 plus h, minus r at that t0, that gives you your change of your vector, difference in those two values, divided by the change of your x value, or your h, that is the change of the independent variable. Let me put it that way, it's not x, it's t. Change of the independent variable, and that would be x. Because that's really down here, t0 plus h minus t0. T0 goes out, we just have the plus h left. Okay. So that's what we mean by the difference quotient that we're using for vector value functions. Okay. Now, yuck. They've got these out of order. This should be next. Okay. So I'll have to remember to go back and show that other slide in just a minute, because that is a slide worthy of note. All right. So here's our difference quotient. Here is your r of t0 plus h. Here's r of t0, and then after a certain length of time h, this is assuming the function is going in this direction. After some little time h, this moves to there, so the difference between those two, r of t0 minus r of t0 plus h minus r of t0, that would be that length right there. Why? Because r of t0 plus this will give you that. Yeah. So that's what it is. Okay. Now, what you're doing is dividing this by that h. Okay. Now, if h is a real small number, dividing by a very small number is basically multiplying by a pretty big number, because of the reciprocal relationship there. So that's why they draw this as extended that way. Now, if h was a pretty large number, it wouldn't have been a very good thing to use, but then that could have shortened that, because if h was larger than 1, then that scales this down. But we're assuming your h is something less than 1, so dividing by h then scales it up. Now, that's not quite a tangent vector, is it? But if you let this h get smaller and smaller and smaller, then this point here goes like this, and it's getting more and more up until finally, when that h approaches 0, guess what you got? The tangent vector. Now, here's something that is hard to see on a two-dimensional plot. Trying to illustrate 3 dimensions is, what direction is that really facing? Is it facing along the board that way, or is it facing out of the board this way, or into the board this way? It's hard to say, but that's a 3-dimensional vector, because you assume the r's are, since you drew them on the 3 space, that is a 3-dimensional vector, and it's going somewhere there. It's just not as easy to see as it was in 2 space. Okay. But the difference quotient points in the direction of that change of r between this point and that point, points in that direction, and that's magnitude. Now that's before you let h go to 0. But you can see that's going to move toward the tangent vector. All right. And I think that's what this slide shows. And it's not going to show it very well unless I split it into pieces here. Okay, first, difference quotient. You can't see it converging, but here's the first. There's r of t0, r of t0 plus h, when h is a hefty enough quantity, less than 1, but hefty enough. Then when you divide that by h, it scales it up. Because this would be the difference. Dividing by a small number h is going to be extending that. Okay? Then, when you let your h get smaller, then that is going to bring this vector up here, and that's going to be still in that direction. Now, here your R of t plus h minus R of t is R of t0 is there. And now notice how it scaled more because your h got smaller. Okay? But of course, you started out with a smaller entity and it was going. You can say again?
It's like scalars until you hit 0.
Yeah. Until you get
Not scalars,
whoops.
secant lines.
Yeah, I'm sorry, I hit the wrong advancement key. So I think what I'll do is just do this part now. Okay, this is the one we just saw, and then as this gets smaller and smaller and smaller, then h getting smaller, then that's approaching the tangent line at that point. Now, the magnitude is the part that's getting crazy, but it's no worse than it was with scalar functions because your numerator is getting small as your denominator is getting small. So this magnitude of this thing is going to 0, and you're dividing by something that's going to infinity because it's going, dividing by something going to 0 is like multiplying by something going to infinity. So it does, if the limit exists, that's going to be the r prime vector, which is the tangent vector to that curve, in whatever direction it happens to be facing, but it converges to some vector r prime of t0, and that's going to be tangent to the curve, wherever that curve is, in whichever direction it's facing in 3 space. Does that kind of make sense? All right. Now I think we go back to this slide. This is the one they had kind of out of order. And I've never been really convinced of the value of this expression here. But the tangent line at r of t0, it is a line. So you should be able to express it as a linear vector function of some single parameter t, and that's going to be the r at t0 plus t times r prime at t0. Okay? And if you think about this, this is kind of like a y-intercept, and this is kind of like a slope, mx plus b, mt plus b. So this is in t, not x. So yeah, that's kind of what it seems like. Now, this isn't really a y-intercept anymore because you're in 3 space, but that's the intercept when that value t is at its initial value t0. That's where it's starting from. And at that point, so whatever that value is plus, that gives you some length plus, and then you're adding to it this, which turns out being kind of like a slope of the tangent, but it is still a vector now, but multiplied by that parameter t. Okay. And again, to me, that formula, it doesn't do a lot for me. I mean, I can see what they're saying, but I'm not sure that it's saying, oh, if they hadn't said that, I wouldn't understand this at all. It's sort of like, because I understand this, I can see where they get this. So it doesn't seem to have any value added here to me. Maybe it does to you. If it does, fantastic. Go for it. Okay. What's that? Yeah. Here's the best I can say. Okay. Notice that's the sum of 2 vectors. Okay. So let's go back to this. No. let's go ahead to this drawing here. Not that one, but this one, okay? Don't zoom in on this one alone. Okay. Now, this is your R of T0, remember? This basically is your R prime. So take this, the R prime that gives you direction, times T, that is your variable, it's not the T0 but T. And this is then going to be your L of T, that's the line that has initial point here, kind of like a y-intercept, not the same, and a slope, basically, or a direction there, and the T is, the magnitude of that slope is then gives you how much a unit change of T is going to give you. It'll be in that direction. So if you wrote the vector here, oops, I can't, because as soon as I write, it's going to shrink. So let me see it. Oops, that's not it. Where did that come from? Yeah, that must be it. Yeah. Okay. Yeah, here we are. Okay. L of T would be this. This is R at T0. Remember, right here, there's our R at T0. And this is your R prime at T0. Plus T times R prime at T0. Okay? So you could think of this as that's your initial point for this quite, but this gives you the initial value where you start from, and then you go in this direction that many units, T, and that gives you your L as a function of T. These are constants, you know, so the T, that's the function of that. I don't know. That's the best I can do with it. And it kind of makes sense to me, but do I ever really use that? Not much. Okay. So let's see if we can do example 5. All right. And this says you need a computer algebra system. Let's hope we don't. Let's see if we can do it without that. I don't think this has a, yes it does. This is that one. Now I'll blow it up for now, but it's one we've seen before, right? Awfully close to one. Well, maybe not exactly, but pretty close. Second? Yeah. So the tangent vectors to the vector R, where here's your displacement vector R of T, your vector R of T, cosine T, sine T, sine 4T. For cosine T squared. Sorry, I can't talk. Now, notice this is the Z component. If you're looking down at that, so you're taking the Z out of the picture here, this forms a circle. These points here plot down into a circle. Okay? Believe it or not, they do. It's what's so hard to see in free space.
I guess I can see it now that you said that.
What's that?
I can see it now that you said that.
Yeah. And the 4 cosine T squared, you can let one of these be a constant, and then you can almost see that, you know, that's what it would be in the other dimension, and that's what it would be in this dimension. So, yeah. All right. I wish they hadn't have done too much of this, because what we needed to do was, it says plot R of t. They've done it for us. Thank you very much. That's probably what you needed the CAS for. Together with the tangent vector at t equal pi fourths and t equal 3/2 pi. Okay? And then it says find a parameterization of the tangent line at t equal pi fourths. That's the first one. So let's do what we would have needed to do if they had just drawn it for us, but that's all they did. Okay? We want the tangent vector at t equal pi fourths. So what would we have to do? Good first step. Second? Second? Take a derivative. All right. I tried to hint as far as I can.
This is calculus.
Okay. And what will this do? That's going to be a vector. Negative sine t, cosine t, 8, you're right, 8, cosine t, chain rule, second, not a t out front, how about a minus sine t? Okay, chain rule is the power function, 2 times the derivative of the 8 times this function, cosine t, times the derivative of that function, cosine t, which is negative sine t, multiplied by. Okay, so there's your r prime of t. All right, now, what we've got to do is find out where in the world are we, Waldo? Okay? When t is equal to pi fourths. So let's start when t is equal to 0. Where are we there? Let's start with r of t. You're at 1,
0,
4. Okay? So for x of 1, now notice how they've got they twisted sort of our thing. There's positive x, there's positive y, there's positive z. Still a right-hand rule, it's fine. But it started over here. So when t is equal to 0, your x is 1 already. So it's out here somewhere, like maybe right there. Your y is 0, so you're still on the x-axis. You haven't moved off the x-axis yet. But then your z moves you up. What do we say? 4. Okay, and there you are. So there you are then, at t equal pi 4.
No, that's a 0.
Huh? No, I'm sorry, that was at 0. I did quite have that right there. Yeah. Without scale on it, it's hard to tell. So it's probably here. It's that point right up there. So that's the maximum this is going to get. Okay, so it's right there. X, come out 1. Don't go any further on y and go up here. Okay. Now, when you go to pi fourths, t equal pi fourths, this becomes square root of 2 over 2. And this becomes
4 square,
okay,
2 square root 2.
Say again?
2 square root 2? Or no, you can
okay. This is square root of 2 over 2. Square it, and you get 2 over 4, which is 1/2, and 4 times 1/2 is 2. Okay. Now, this probably doesn't look like it, but you've gone out here, square root of 2 over 2. Now, before you went out 1, square root of 2 over 2 is 0.7, isn't it? Yeah, square root of 2 is 1.414, and this is around 0.7. So it's about 0.7, not as far out as you were here, but then you go up here, and that point, well, somewhere there is that, and then you go up, what do we say, 2? And it doesn't look like, it looks like that's going more than 2. If this is 4, that looks like, but remember we're going that way on the plane, so that isn't as far up as what it seems. That's half the distance, okay? Now, there's your point, t equal pi fourths. There's where we are. Now, what it's asking for is the, was it tangent vector? Plot that with its tangent vectors at t equal pi fourths. So the first thing we need is, or one thing we need is the derivative at pi fourths. So at pi fourths, what's this? Negative square root of 2 over 2. Square root of 2 over 2. So that x is going that way, okay? The y is going that way, and this is going down, okay?
Sure.
Well, no, let's see. No, it's square root of 2 over 2, that's positive and that's positive. That was a negative, so that's going to be going down in z, but it sure doesn't look like that's quite as much angle as we ought to have. But then to the parallax is getting to us. Basically, these are pointing from here to there is pointing toward the origin, and sure enough, it seems like it is. Okay, the x's and y's are going in this line here, and then you're going down much faster than what that's coming in, and that's, and let's see, this would be square root of 2 over 2, square root of 2 over 2, so that'd be, again, 1/2, and 1/2 of negative 8 would be negative 4. So it's that minus 4 and a minus on x, minus 0.7, positive 0.7 on y, that's a little, yeah, positive 0.7 on y, that one I can't quite see in this thing, and then down 4, negative 4. So yeah, it's a great deal further. Thank you for drawing this because I would not have seen that, but that is indeed the tangent line there. Now, what we haven't done is written them. We just sort of looked at them, and that's all it says to do is plot them. Okay, let's do it for 3/2 pi. Where are we when t is 3/2 pi? Cosine of 3/2 pi is 0. No, you're right. Cosine of 0 is 1. Half of pi is 0. Pi is negative 1. 3/2 pi is 0 again.
Right.
Cosine is 0. So that's a 0.
And then sine would be negative.
So on x, you're doing, yeah. Sine would be a negative 1. So your y value is at negative 1. And your z value is 0. So sure enough, we're right here on the y-axis, negative 1 out here. Okay? Now what we got to figure out is which way we're going. And by the way, remember this point is directly over the x-axis because the y is 0 here. So since you're going in that direction, yeah, that has to be a positive y. Okay, so yeah, that's seeming reasonable. Positive y, negative x, positive y, because this is literally coming back in x. It looks like it's going out in x. It's not. That's going back in x, over in y, but back in x. Okay, and going down in z. So this one is, yeah, we just said it right there. Now let's look at some derivative there. The x component is in negative, no, wait. Sine of 3/2 pi is what? Just said it earlier. Negative 1, but you got a minus s, so it's a positive 1. This is 0, and that's 0. So sure enough, there's a positive 1 in this direction when it's off here by positive 1. So those
If you looked at that as just an XY plane,
right.
looking down the axis, that'd be a unit circle.
Yes, exactly. Right. This part would be. And up here you're going that way in the unit circle. You know. But of course the actual thing is going like this. So that's why it's moving in that direction. So you got that. Now, with them doing the hard work, drawing the graph, and even putting those in, but we had to verify they were right, it says, find a parameterization of the tangent line at t equal pi fourths. A parameterization of that tangent line. Okay? So what we mean by that is using that thing we did before, L of t is equal to, was it V? No, R. Yeah, R of t0 plus t times r prime at t0. Okay? Thinking of that as kind of like it's not a y-intercept, but some initial point, and this is the slope heading in the direction of, multiplied by your variable. That's what they're looking for here, this L of t. So what is your R of t0 at pi fourths? What is R at pi fourths? We just did it earlier. R at pi fourths is, what did you say? Square root of 2 over 2, square root of 2 over 2, what was the third component? Wasn't it a 2? Yeah, I believe it was. Okay, because square root of 2 over 2 squared would be 1/4. So that would only be 1, wouldn't it?
Yeah, it would only be
1, okay, right. I was thinking of the first point. That's 1. No, yeah. Wait. No, square root of 2 over 2 times square root of 2 over 2 is 1/2. 2/4, which is 1/2. So the 2 was right. Okay. Messing with my mind here. Okay. Only it's a, no, it's a positive. Yeah, the R is positive. R prime is negative there. R is positive. Okay. So that's what we've got here. This is our vector, square root of 2 over 2. Square root of 2 over 2. 2. Plus, t is the parameter, okay, you're doing a parameterization, and this would be, what vector is that? Yep, and that was? Yeah. Negative square root of 2 over 2. Square root of 2 over 2. That was the negative 4, wasn't it? Let's make sure. Yeah. 1/2. Yeah. Okay. So this L of t would be the x component, square root of 2 over 2 minus t times the square root of 2 over 2, comma, square root of 2 over 2 plus t times the square root of 2 over 2, comma, 2 minus 4t. Now, that's, if you write it out, guess what they did? They left it just like this. Okay.
So you can see the form.
Yeah. I mean, that's a parameterization as well, but I thought they wanted it written out as a vector with the parameter in it, but it is, those are the same. All right, does that kind of make sense? Okay. Let's move on to example 6. I think this is this next slide here. Let's take a look at it first. I think, now I don't know why the, why the legend and the graph are so wacko here, but why aren't they under each other? I don't know. but this is your, this is called the cycloid. Okay. Have we had that before? Okay. Basically, this would be, put a light stick on the rim of your tire, not so it gets run over, but right on the rim, and then drive down and watch the patterns that light stick makes. When the tire, when it's on the ground, it's right there. As the car is moving this way, it picks up and goes up to the top of the tire, and then comes down to the ground again, up to the top of the tire. Here it's at the, even with the axle in there, it's even with the axle. That's the pattern it makes. It's a cycloid. Okay. One way to picture it, I guess. Do a slow release camera shot, everything's dark except for the light stick, and you'd see that pattern. Okay. Second, yeah. I have a piece of paper there, and the marker is marking on the piece of paper. You drive very straight. Okay. All right. This is the function for it. For our cycloid, and of course when I go to write, it's going to shrink. And this will be 10. Okay. Why is it not? Okay, there it is. It's hanging on to being a laser point. Here's the function, r of t, this is for a cycloid, is equal to strange vector t minus sine t, comma, 1 minus cosine t. Two-dimensional. We're not doing three-dimensional cycloid. Please don't. Okay. That traces a cycloid. Find the points where A, R prime is horizontal and non-zero. R prime of t is horizontal and non-zero. Okay. Now, it may seem to you at first glance that's can't be true. Usually we think where it's horizontal, R prime is 0. Not necessarily. So let's guess what we would do first. Let's find out what R prime is anyway. R prime is equal to, you tell me. How about that t there? Huh? Yeah, okay, I thought you said, okay, I didn't hear you say 1. 1 minus cosine t. That's correct. That's the first component.
And then that would just be sine t.
Sine t. Okay. There is your parametric equation for your vector equation for your first derivative function. Okay. And we want to know where that is horizontal. Now, what do we mean by it being horizontal?
Parallel to the x-axis.
Okay, yeah, we're dealing in 2 dimensions there, so it's parallel to the x-axis, which means the y is not changing, right? So basically what we're saying is that this is 0. Where is that 0? Okay, not just pi. It is at pi. Is that the only place? No.
Pi halves would be 0.
0, pi. Yeah, and then n pi.
Yeah.
Okay. But that's where it's horizontal, where the y is not changing, but where that y is non-zero. Okay? Let's see, where the slope, where the R prime is non-zero. Okay? Well, where would that be 0?
Right, so that'd be pi.
Okay?
Every odd number of pi's.
Yeah, okay, well, let's think. We've got, these are the values where sine t are 0.
Whatever cosine
Okay.
t is 1.
Wherever cosine t is 1, and where is that true?
At 0.
At 0,
3 pi.
at 3 pi, because at 2 pi it's, I'm sorry,
No, it'd be 2 pi.
yeah, it would be 2 pi. Whoops.
So just every 2 pi.
So it would be, this would be 0 every time cosine, yeah. So that would be at 2 pi, 4 pi. Okay. Now, where x is 0, y is 0, that's where r prime is 0. Okay? But we want where r prime is horizontal, but non-zero. So you throw out this one and the even pies, and you have the odd pies left. And that would be pi, 3 pi, 5 pi. So horizontal, but non-zero. Okay. See, come here, your first derivative is,
Vertical.
yeah,
Wait, or is it
basically
plus?
what you have, your slope is 0 over 0,
Yeah, it's,
which is undefined.
so there isn't.
Yeah, it's either positive infinity or negative infinity, and it's the same, it's that, those at the same time. So yeah, those it's undefined. So at your odd pies, your first derivative is your, yeah, they say it right. I thought this was just saying R is horizontal. R prime is horizontal, but it's not non-zero value. Okay, because it does have a vertical. Down here, they're both 0, and that's where your tangent line would be undefined. Okay. Are we running out of time?
Yeah, like a minute and a half.
Oh, okay, we got some time then. All right, that was the A part. The B part says where R prime is the 0 vector. And I think we just answered that one too. Those would be the even pies. Okay. All right. Let's see. Conceptual insight. I think is the same picture here. Notice at the cusp, the R prime is not defined, basically, because, or the slope of R prime is not defined. R prime is these values, but the slope is not defined because that would be y over x for those values, and that would be either, like you said, positive or negative infinity. Everywhere else, the slope is defined, but not there. Even lies can't be. I think that's all the conceptual insight is talking about. Okay. Now, we didn't have time to do example 7, so we'll pick up there next time. Looks like a good place to begin. And let me see if we got any homework exercises. Yes, I think we did. Okay. Do number 1. Do either 3 or 5. Wait, I'm sorry, looking at the wrong page. Any of the odds 1 through 5, any of the odds 7 through 11, either 13 or 15 or both. Let's see, make sure I'm not going to give you any we haven't done yet. Any of the odds 17, either 17 or 19 or both. Do 21. Either any of the odds 20 or either 23 or 25 or both. 27, do 27. And I think you can do any of the odds 29 to 33, and we'll hold there. Pick up the rest of them next time. Oh, yeah. Any who came in late, if you didn't get a test, be sure you get your test. And before you go, I can tell you what sections these are covered by. All the rest of you get your test. Did you get a test? Yeah, it was the chapters the 11 and 12 test. Okay. If you'll hang on just a minute, I will tell you which sections these are from. Okay? One is from 11:1. He's fishing, okay? Two is 11:2. 3 and 4 are 12:1. 5 is 12:2. 6 is 12:3. 7 is 12:4. 8 is 12:5. 9 and 10 are from 12:6. Got it? Okay, good deal. I guess I need to send that to Javon. Not with me. The ones that were in this room were either broken or jammed. This one's... Okay, what is it you had? Your paper, I can take it. I can staple it when I get down to my office. This one, I don't have anything strong enough to pry it open without breaking it, so that's why I haven't tried too hard on that. All right, let me shut this down.